The ocean begins long before humans ever saw it. It begins about 4.4 billion years ago when Earth was still a glowing ball of molten rock wrapped in a sky of steam. The first water arrived as ice wrapped around dust grains in the solar nebula and as water-rich comets slamming into the young planet. Some of it was already here, locked in the minerals of the mantle, exhaled through volcanic vents as the crust cooled. By the time the Great Bombardment ended, Earth had its oceans, hot, acidic and mineral-rich, covering almost the entire surface in a global sea deeper than anything we have today. That primordial ocean had no continents, no tides driven by a moon because the moon had not yet been born from the colossal impact that tore a chunk of Earth away. The water was green with dissolved iron, the sky orange with carbon dioxide and methane. Ultraviolet light poured through an ozone-free atmosphere and split water molecules high above, letting hydrogen escape into space while oxygen slowly began to accumulate. Life probably started in those warm, shallow alkaline vents where hydrogen-rich fluids met carbon dioxide-rich seawater, building the first simple organic molecules that learned to copy themselves. Fast forward a few 100 million years and the first continents began to rise, tiny archipelagos of granite bobbing like corks on the mantle. The ocean was still everywhere, but now it had edges. The water cycle began. Evaporation, rain, rivers carving channels, minerals washing back to the sea. Salt accumulated because rivers bring in sodium and chlorine, but almost nothing takes them out again. By 4 billion years ago, the ocean was already salty, though not quite as salty as today. The Great Oxygenation Event around 2.4 billion years ago turned the seas from green to blue. Cyanobacteria had been pumping out oxygen for centuries, but at first it rusted the iron dissolved in the water, forming the vast banded iron formations we mine today. Only when the iron was used up did free oxygen finally enter the atmosphere and the upper ocean. Creatures that could not handle oxygen died. Those that learned to breathe it took over. For the next 1.5 billion years, the oceans were ruled by microbes. Stromatolites built towering reefs in shallow water, layer upon layer of bacterial mats trapping sediment. The sun burned 30% dimmer, yet the greenhouse effect kept the seas from freezing. Ice ages came and went, sometimes covering the entire planet in snow and ice so thick the oceans nearly stopped circulating. Then, around 650 million years ago, something changed. The Ediacaran organisms appeared, soft, frond-like creatures anchored to the muddy bottom, absorbing nutrients directly from the water. Some looked like discs, others like tubes or bags. They were the first animals, or at least the first things big enough to leave fossils. A few tens of millions of years later, the Cambrian explosion rewrote the rules. Skeletons, eyes, legs, mouths, predators, all appeared in a geological blink. Trilobites scuttled across the seafloor. Anomalocaris, a meter-long shrimp from nightmares, hunted with grasping claws. The ocean became a very dangerous place to be small and soft. Through the Paleozoic era, the seas rose and fell as continents collided and ripped apart. Warm, shallow seas flooded the interiors of supercontinents, leaving limestone layers hundreds of meters thick full of brachiopods, crinoids, and corals. Goniatite ammonites with complex sutures swam above reefs built by rugose and tabulate corals that looked nothing like modern ones. Fish evolved jaws, then bones, then lungs for gulping air in stagnant pools. Some crawled out onto land and never came back, but most stayed, evolving into sharks, bony fish, and eventually the giant marine reptiles of the Mesozoic. When the Chicxulub asteroid struck 66 million years ago, it boiled huge sections of the ocean, triggered tsunamis hundreds of meters high, and filled the atmosphere with sulfur that blotted out the sun for years. 90% of marine species vanished almost overnight. Ammonites, mosasaurs, plesiosaurs, most plankton, gone. The ocean turned acidic as dissolved carbon dioxide levels skyrocketed. Yet within a few 100,000 years, diatoms and coccolithophores exploded in number, pulling carbon back down and restarting the food chain from the bottom. Whales evolved from small deer-like creatures that waded into rivers 50 million years ago. Step by step, they lost their hind legs, grew gigantic, and reconquered the seas their ancestors had left. Baleen whales became the largest animals ever to exist, filtering krill by the ton. Sperm whales dove deeper than submarines, hunting giant squid in the eternal dark. Meanwhile, the configuration of the continents kept shifting. The closing of the Isthmus of Panama 3 million years ago separated the Atlantic and Pacific, changed circulation patterns, and helped trigger the ice ages that have dominated the last 2.5 million years. Cold water sank at the poles and crawled along the bottom toward the equator, returning warm at the surface, the great conveyor belt that keeps Europe mild and drives global climate. Today, the ocean is stratified into layers like a cosmic cake. The top 100 meters or so is the mixed layer, warmed by the sun and churned by wind. Below that lies the thermocline, where temperature drops sharply. Light fades to nothing by 1,000 meters. Pressure increases by 1 atmosphere every 10 meters. At the bottom of the Mariana Trench, you are crushed by more than 1,000 times the air pressure at the surface. The epipelagic zone, from the surface to 200 meters, is where almost all photosynthesis happens. Phytoplankton, single-celled drifting plants, turn sunlight, carbon dioxide, and nutrients into sugar and oxygen faster than all the forests on land combined. Zooplankton eat them, small fish eat zooplankton, big fish eat small fish, and so on up to tuna, sharks, and whales. Below 200 meters, the twilight zone begins. No sunlight means no plants, only animals drifting or swimming through the dark, many glowing with bioluminescence to attract prey or mates. Lanternfish, bristlemouths, viperfish, billions upon billions of small fish with light organs and enormous mouths full of needle teeth. This is the largest vertebrate biomass on Earth, yet almost nobody ever sees them because they live too deep for nets and too shallow for deep submersibles. Drop another 3,000 meters and you reach the bathypelagic, the midnight zone. Everything here is slow. Food falls as marine snow, dead plankton, feces, abandoned jellyfish houses, and whatever is not eaten on the way down arrives as sparse flakes. Anglerfish females carry tiny parasitic males attached to their bodies. Gulper eels have mouths bigger than their bodies. Tripod fish perch on the bottom with stiffened fins like landing gear, waiting for something edible to drift past. The abyssal plains begin around 4,000 meters. They cover more area than all the continents combined, flat as parking lots under kilometers of water. The sediment is mostly clay and the tests of dead plankton, accumulating a few millimeters every 1,000 years. Sea cucumbers plow through it like living vacuum cleaners. Glass sponges build lattices that last centuries. Xenophyophores, giant single-celled organisms the size of dinner plates, create intricate tests out of mud and minerals. Below 6,000 meters you enter the Hadal zone, the trenches. Here the rules change again. The water is near freezing, the pressure immense. Yet life thrives. Amphipods swarm over bait fallen from above, tearing chunks with scissor-like claws. Snailfish swim lazily, their bodies floppy and gelatinous to avoid being crushed. Bacteria metabolize sulfur from the rocks. Every trench has its own unique community, isolated by ridges and currents. Along mid-ocean ridges, new crust is born. Magma rises, cools, and spreads sideways at a few centimeters per year, pushing continents apart. Black smokers erupt superheated water rich in metals, building chimneys that grow meters in a decade. Tube worms, a meter-long wave red plumes full of symbiotic bacteria that turn hydrogen sulfide into sugar. Crabs, shrimp, and eyeless fish graze the bacterial mats. Cold seeps on continental margins leak methane and oil. Giant mussels and clams harbor sulfide-loving bacteria inside their gills. Sleeper sharks cruise slowly, picking off anything that moves. Coral reefs occupy a tiny fraction of the ocean but explode with color and life. Fish in every shade of the rainbow dart between branches of staghorn and brain coral. Sharks patrol the drop-offs, At night, the reef changes completely. Corals spawn in synchronized clouds of eggs and sperm. Parrotfish secrete mucus cocoons. Octopuses hunt by color-changing camouflage. Kelp forests along cold coasts grow meters in a single season, creating underwater cathedrals where sea otters wrap themselves in fronds to avoid drifting away while they sleep. Sardines form bait balls the size of apartment buildings, twisting like living tornadoes as dolphins and seabirds attack from every direction. Mangroves line tropical shores, their tangled roots trapping sediment and providing nurseries for countless baby fish. Seagrass meadows stabilize the bottom and sequester carbon faster than rainforests. Salt marshes stink of sulfur yet feed half the commercial fisheries on the planet. The Arctic Ocean is the smallest and shallowest, mostly covered by sea ice that reflects sunlight and keeps the planet cool. Under the ice, an entire ecosystem clings to the underside: algae, copepods, Arctic cod, ringed seals, polar bears. As the ice retreats, killer whales move in, hunting narwhal and beluga that have never seen them before. The Southern Ocean circles Antarctica with nothing to stop the wind. The roughest seas on Earth generate waves taller than apartment buildings. Beneath them, krill swarm in numbers that turn the water red. Penguins porpoise through the waves. Leopard seals wait to ambush them. Colossal squid battle sperm whales in the depths. Currents tie everything together. The Gulf Stream carries warm water from the Caribbean to the North Atlantic, keeping Norway ice-free, while Canada at the same latitude is frozen solid. The equatorial countercurrents, the California Current, the Humboldt Current, each brings nutrients or warmth that dictates where fish gather and where deserts form on land. Upwelling zones where deep water rises bring nutrients to the surface and trigger plankton blooms visible from space. Off Peru, off Namibia, off California, these cold, foggy coasts support some of the richest fisheries on Earth. The ocean also holds history. Ambergris from sperm whales washes up smelling of the deep past. Glass fishing floats from Japan drift across the Pacific for decades. Messages in bottles still turn up after a century. Shipwrecks from Phoenician traders to nuclear submarines litter the bottom, each a time capsule slowly dissolving. We have named only a fraction of what lives down there. Every deep-sea expedition brings back organisms that defy classification. Scale worms with iridescent bristles. Sea pigs that walk on water-filled legs. Jellyfish that pulse like UFOs. Dumbo octopuses flapping ear-like fins. Vampire squid turning themselves inside out in a cloak of false eyes. Sound travels farther in water than in air. Whales speak across entire ocean basins. Shrimp snap claws loud enough to stun prey. Dolphins echolocate with clicks sharp enough to kill small fish. The ocean is never silent. It hums with life. Yet it is also dying in places. Coral bleaching turns reefs bone white. Dead zones spread where fertilizer runoff feeds algae blooms that rot and consume oxygen. Bottom trawlers scrape the seafloor bare, turning three-dimensional habitats into mud flats. Plastic bags drift like jellyfish, choking sea turtles. Acoustic pollution from ships and sonar disorients whales, driving them to beach themselves. Still, the ocean is vast beyond comprehension. A single current can carry more water than all the rivers on Earth combined. A blue whale's heart is the size of a small car. A teaspoon of seawater contains millions of viruses and thousands of bacteria, most unknown to science. We have sent robots to the bottom of the Mariana Trench, mapped hydrothermal vents with autonomous submarines, sequenced DNA from a cup of seawater that reveals hundreds of species never seen. Satellites watch the surface in real time, measuring temperature, height, color, and roughness down to centimeters. But every answer reveals 10 new questions. Why do some trenches have snailfish and others do not? How do whales navigate thousands of kilometers without landmarks? What lives under the ice shelves of Antarctica, cut off from the sun for millions of years? How many ecosystems have we destroyed before we even knew they existed? The ocean has survived snowball Earth, massive volcanism, 5 major mass extinctions. It has seen continents rip apart and smash together. Sea levels rise and fall by hundreds of meters. It has absorbed comets and asteroids, soaked up carbon for eons, given us the air we breathe. It is older than the mountains, deeper than our dreams, more alive than we can imagine. It covers 71% of our world yet remains 95% unexplored. Every dive, every sonar sweep, every net hauled up from the dark reminds us how little we truly know. And still the waves roll in, the tides rise and fall, the currents turn, and the great blue heart of the planet keeps beating, keeping us alive while hiding its deepest secrets in plain sight just beyond the shore. The ocean is not one thing. It is thousands of oceans stacked on top of one another, separated by temperature, salinity, density, light, and pressure. To understand it properly, you have to descend layer by layer, the way a submersible does, watching the world change every few hundred meters. Start at the surface on a calm day. The water is warm, almost body temperature in the tropics. Sunlight spears down invisible shafts full of drifting particles. Phytoplankton, mostly diatoms, dinoflagellates, and tiny coccolithophores, are blooming in uncountable trillions. A single liter of this water can contain 10 million living cells. Some are armored with silica shells so intricate they look machined. Others carry whip-like flagella and can swim against currents. A few, like Noctiluca, glow electric blue when disturbed. These organisms fix more carbon every year than every tree on land put together. Without them, the atmosphere would have 30% more CO2 and we would cook. Zooplankton graze them. Copepods the size of rice grains, krill with glowing red eyes, arrow worms with spines that snap shut like bear traps, larvae of everything, fish, crabs, starfish, worms, drift helpless in the current, many looking nothing like their adult forms. A baby eel is a flat, transparent leaf called a leptocephalus. A baby octopus is a miniature adult with only 3 heartbeats per second instead of 1 per second. Everything is eating everything else. A tuna can cross an ocean basin in weeks, burning energy like a missile, chasing sardines that school so densely they turn the water silver. Dive deeper. At 50 meters, the light shifts from white to green. Red wavelengths are gone, absorbed. Anything red, coral, blood, a diver's mask, looks black. Many deep fish evolved red skin or red light organs because red is invisible here. It is perfect camouflage. The pressure is now 6 atmospheres. Your ears would pop constantly if you were breathing air. At 200 meters you cross into the mesopelagic, the twilight zone. Sunlight is a faint memory. Only blue penetrates this far. Most animals are black, silver, or transparent. Many have downward-facing light organs that erase their silhouette from predators below, a trick called counterillumination. Hatchetfish look like mirrored knives. Dragonfish have barbels that glow to lure prey within reach of jaws lined with fangs so long they cannot close their mouths fully. Some species produce red light, again invisible to almost everything else, and use it like a sniper scope. Food becomes scarce. The rain of marine snow, dead bodies, fecal pellets, abandoned mucus houses, takes weeks to sink this far. Many animals here have huge mouths and elastic stomachs. A single meal might be their last for months. Some, like the stoplight loosejaw, can unhook their jaws and swallow prey larger than themselves. Others shrink their own organs between meals to save energy. Temperature drops fast. In most of the ocean, the thermocline is a sharp boundary where warm surface water sits on cold deep water like oil on vinegar. Cross it and you fall 10 degrees Celsius in 100 meters. Your dive computer would scream. At 1,000 meters you are in the bathypelagic, the midnight zone. No light at all, ever. Pressure is 100 times surface air. The water is usually 2 to 4 degrees Celsius, cold enough that metabolism slows to a crawl. Animals grow slowly and live long. A deep-sea blackbelly rosefish can be 40 years old and still not mature. Some grenadiers live over 150 years. Many animals here never touch the bottom. They just hang in the water column, waiting. Siphonophores, colonies of specialized clones, form living fishing nets dozens of meters long. The Portuguese man-o'-war is the most famous, but its deep cousins are far larger and more delicate. One species, Praia dubia, reaches 50 meters, longer than a blue whale. Bioluminescence is everywhere. 90% of animals here produce their own light using luciferin and luciferase in chemical reactions that are nearly 100% efficient. No waste heat. Flashes, glows, sparkles, searchlights, lures, burglar alarms. A predator disturbs a cloud of glowing plankton, and suddenly everything nearby knows exactly where it is. Drop another 2,000 meters and the bottom finally appears, usually as endless flat abyssal plain. 5,000 meters down. The sediment is red clay mixed with microscopic shells. It accumulates 1 millimeter every 1,000 years. Footprints made today would still be visible in the year 3000 AD. Sea pigs, pink sea cucumbers with water-inflated legs, walk in herds, vacuuming the surface. Rat tails with huge eyes and tapering bodies nose along looking for anything that smells like food. Xenophyophores, single cells the size of grapefruits, build castles of glued-together mud grains and sponge spicules. Occasionally the plain is interrupted by a seamount rising thousands of meters from the abyss. These underwater mountains deflect currents, creating upwellings that feed dense communities of filter feeders, corals, sponges, crinoids, things that look like Jurassic relics because they mostly are. Some seamounts have never been visited. We know they exist only because satellite altimetry detects the tiny bulge they make in sea level. Mid-ocean ridges cut through the plains like seams on a baseball. Here the crust is splitting and new seafloor is being born. Lava erupts along the axis, cools into pillow basalt, and spreads sideways at the speed fingernails grow. Hydrothermal vents line the ridge, black smokers, white smokers, diffuse flow. Water forced down into cracks meets magma, heats to 400 degrees Celsius, dissolves metals and sulfur, then blasts back out loaded with minerals. Chimneys grow fast. Some reach 30 meters in a decade. The water is acidic enough to dissolve a human body in hours, yet life thrives. Tube worms 2 meters long anchor themselves to the rock. They have no mouth, no gut, no anus. Inside their bodies live symbiotic bacteria that oxidize hydrogen sulfide for energy. Blood carries oxygen and sulfide in separate molecules to avoid poisoning. The red plume is not a feather. It is a gill packed with hemoglobin. Scalyfoot gastropods armor themselves with iron sulfide scales, actual metal armor grown biologically. Riftia worms can grow a meter in 2 years, faster than any other marine invertebrate. Away from the ridges, on the continental margins, cold seeps leak methane and hydrogen sulfide. Here the symbionts use different chemistries. Mussels the size of dinner plates cluster around the flows. 2-meter-long tube worms related to beard worms wave in forests. Hagfish slime the cracks, waiting for something to die. In the trenches things get extreme again. 10,000 meters pressure over 1,000 atmospheres. Water is compressed so much it is denser than at the surface, yet still liquid because the cold and salt keep it from freezing. Amphipods, shrimp-like crustaceans, grow to 30 centimeters and swarm any bait like piranhas. They have been filmed tearing apart a dead alligator in hours. Snailfish, soft and pink, swim through the crushed depth that would implode a nuclear submarine. Their cells have special proteins, osmolytes, that prevent pressure from denaturing their enzymes. Every trench is different. The Mariana Trench has liquid carbon dioxide pools and sulfur lakes. The Tonga Trench has the fastest plate subduction on Earth, swallowing crust at 24 centimeters a year. The Peru-Chile Trench is filled with sediment so thick that vents are buried and life is sparse. Back up in the shallows, the continental shelves are the most productive real estate on the planet. Sunlight, nutrients from rivers, upwelling all combine. Kelp forests off California grow a meter a day. Sea otters crack urchins while wrapped in kelp to stay put. Coral reefs in clear water build calcium carbonate skeletons faster than almost any other biological process. A healthy reef grows several centimeters a year vertically and harbors 1,000 species in a square kilometer. Estuaries mix fresh and salt water. Oysters filter 30 liters an hour, clarifying the water. Mangroves drop roots like curtains, trapping sediment and protecting coasts from storms. Baby sharks, grouper, snapper, tarpon, all hide among the roots until big enough to face the open sea. The ocean also has weather. Internal waves hundreds of meters high propagate along density layers, invisible from above but capable of moving submarines like toys. Turbulent eddies the size of countries spin off currents and persist for months. Rogue waves, walls of water twice the height of surrounding seas, appear without warning and have snapped supertankers in half. El Niño and La Niña flip the Pacific every few years. When the trade winds weaken, warm water sloshes east, shutting down upwelling off Peru and starving anchovy fisheries while bringing rain to deserts. The entire planet feels it: drought in Indonesia, floods in California, weak monsoons in India. The Atlantic has its own oscillator. Every few decades the conveyor belt slows or speeds, shifting heat and changing hurricane frequency. The last time it shut down completely was 14,000 years ago. Europe cooled 15 degrees in a decade. Ice dominates the poles. Antarctic bottom water is the densest water on Earth, formed when sea ice freezes and excludes salt, creating brines that sink to the abyss and fill the global deep ocean. It takes 1,000 years for a water molecule to go from the Weddell Sea, crawl along the bottom past Australia, upwell off California, and return south. Greenland meltwater is now pouring in fast enough to measurably slow the Atlantic overturning. If it stops, the consequences are unknown but not good. The chemistry is changing too. CO2 dissolves into seawater, forming carbonic acid. Since the Industrial Revolution, the ocean has absorbed a third of our emissions, dropping average pH from 8.2 to 8.1, a 30% increase in acidity. Corals, oysters, pteropods all build shells of calcium carbonate and all are struggling. By 2100, surface water could be more acidic than any time in 50 million years. Heat is pouring in as well. The ocean has taken 93% of global warming energy. Warm water expands. Sea level has already risen 25 centimeters since 1900 and is accelerating. Entire nations are planning their disappearance. Oxygen is declining. Warmer water holds less dissolved gas. Dead zones, hypoxic areas, now cover a combined area larger than the United Kingdom every summer. Fish flee, crabs suffocate, jellyfish take over. Yet life adapts. Some corals are moving poleward. Cold water Lophelia reefs off Norway grow slowly but are thriving. Bacteria evolve to eat plastic. Fish in overfished areas grow faster and mature younger. We are mapping faster than ever. The Seabed 2030 project aims to have the entire ocean floor charted at decent resolution by 2030. Autonomous sail drones, floating robots, and new sonar on fishing boats are closing the gaps. Edna, collecting a bottle of water and sequencing everything that left DNA behind, reveals species hundreds of kilometers away. Submersibles are improving. Carbon fiber hulls, lithium batteries, and 4K cameras now let private vehicles reach full ocean depth repeatedly. In 2024 alone, more people went to the bottom of the Mariana Trench than in the previous 60 years combined. We are finding things we never expected. Glass sponge reefs off Canada as large as cities, thought extinct for 100 million years. Octopus nurseries at 2,000 meters where thousands of females brood eggs on hydrothermal vents, dying when the young hatch. a layer of purple bacteria 2,000 meters down in the Mediterranean living off dim red light from a salt crust. Whale falls, sunken carcasses, create ecosystems that last decades. First hagfish and sleeper sharks strip the flesh. Then zombie worms with green roots dissolve bone. Finally, bacteria mats and limpets persist for 50 years on sulfides from the rotting skeleton. The census continues. In 2024, a single tow of a net off New Zealand brought up 40 new species of mollusks. In 2025, a robot in the Clarion-Clipperton zone found a translucent octopus that broods its eggs for years, the longest parental care of any animal. We are racing extinction and discovery at the same time. The last uncontacted tribes on land can be counted on fingers. In the ocean, there may be millions of uncontacted species. Every drop of seawater has traveled the world. A molecule that evaporates off Tonga today may freeze into Antarctic ice next year, sink to the bottom for 1,000 years, then resurface off Iceland and rain onto Greenland. The ocean does not care about borders, flags, or centuries. It has been here 4 billion years and will be here long after we are gone. Blue and restless, full of voices we have barely begun to hear. The deeper you go into the ocean, the stranger time itself becomes. At the surface, a day is a day. Sun rises, plankton bloom, fish feed, night falls, everything migrates up or down. But descend just a few thousand meters and seasons blur. At 5,000 meters on the abyssal plain, the only calendar is the slow rain of corpses from above. Spring in the North Atlantic means a blizzard of dead phytoplankton that takes 4 to 6 months to reach the bottom. A whale that dies in summer might land in winter. Time is measured in millimeters of sediment and centuries of growth. Some animals down there have life cycles that make trees look impulsive. Orange roughy, a deep water fish with delicious white flesh, do not even reproduce until they are 30 or 40 years old and can live past 250. We only discovered this after we had already fished entire populations to commercial extinction. The adults we caught in the 1980s and 1990s were born when Mozart was still alive. A Greenland shark swimming today in the North Atlantic may have been born during the reign of Queen Elizabeth I. We know this because we carbon dated their eye lenses in 2016. The oldest was 392 years, plus or minus 120. They grow less than 1 centimeter per year and only reach maturity around age 150. Glass sponges in the Antarctic can live thousands of years. One reef off East Antarctica is estimated to be 12,000 years old, older than any human civilization, built by animals that look like delicate Victorian lampshades made of silica needles. They grow so slowly that a single specimen the size of a person may have started life when woolly mammoths still walked the planet. Corals are the same. A black coral colony in Hawaii was dated to 4,265 years old. It was a young bush when the pyramids were built. We cut it down for jewelry. Even bacteria have their own time. In the mud 300 meters beneath the seafloor of the Pacific, microbes divide once every 1,000 years. They are not dead. They are just waiting. Some of those cells may have been buried when the first dinosaurs appeared. Their metabolism is so low that repairing one DNA break takes decades. Now rise back up and look at the fastest lives in the sea. Some jellyfish and salps live only a few months but clone themselves so fast that a single individual can become a blooming cloud of millions in weeks. The immortal jellyfish, Turritopsis dohrnii, can revert its adult body back to a juvenile polyp when stressed, theoretically living forever if nothing eats it or it avoids disease. We have no idea how common this trick is in the deep. We only found it because one species washes into labs. Phytoplankton can double in a single day under the right conditions. A red tide of Carenia brevis off Florida can go from undetectable to 1 million cells per liter in 48 hours, poisoning fish, manatees, and humans who breathe the aerosol. Squid grow faster than anything with a backbone. Humboldt squid in the eastern Pacific can add a kilogram of body mass per month and reach 20 kilograms in 18 months. They live hard and die young. Almost none survive past 2 years. The ocean is full of these mismatched clocks all running at once. Let us follow one drop of water on its full journey through the great conveyor belt. Imagine a droplet that forms when sea ice freezes in the Weddell Sea, Antarctica, in the year 1450 AD. Salt is excluded. The remaining water becomes dense and cold, -2 degrees Celsius, and sinks straight to the bottom, 4,000 meters down in a matter of days. It joins Antarctic bottom water and begins crawling north along the seafloor at walking pace, 3 to 5 centimeters per second. It flows into the Argentine basin, slips past the Romanche fracture zone, enters the Brazil basin, rounds the tip of Africa, and enters the Indian Ocean abyss. By the time it reaches the Crozet Plateau, it is already 300 years old. It continues north, fills the deep basins of the Arabian Sea and Bay of Bengal, then turns east, crosses under Indonesia, and enters the Pacific, the largest body of water on Earth. It takes another 400 years to creep up the western Pacific, past the Mariana Trench, under Japan, past the dateline. Around the year 2400 AD, it finally reaches the North Pacific abyss. There it slowly rises, warmed a fraction of a degree by geothermal heat leaking from the crust. It spirals up through the dark, mixing with younger water, until it reaches the sunlit zone off Alaska or Kamchatka around the year 2800 AD. Now it is warm enough to evaporate. It rises into a cloud, blows across Canada, falls as rain on the Great Lakes, flows down the St. Lawrence, re-enters the Atlantic, rides the Gulf Stream to Europe, cools again off Greenland, and is ready to sink once more. 1,000 to 1,500 years for a single circuit. That is the heartbeat of the planet. Every major current has its own personality. The Gulf Stream is a river in the ocean, 80 kilometers wide, a kilometer deep, flowing at 4 knots near the surface off Florida, faster than most rivers on land. It carries 25 times more water than the Amazon. Satellites can see its heat signature from orbit, a blue ribbon of warm water cutting through colder green. It splits off the North Atlantic current that keeps Ireland green and Norway's ports ice-free in winter. The Antarctic circumpolar current is the mightiest, circling the globe with nothing in its way, moving 150 million cubic meters of water per second, more than 100 times all the rivers on Earth combined. It links the Atlantic, Pacific, and Indian Oceans into one continuous system and isolates Antarctica in a cold embrace. The Kuroshio off Japan is the Pacific's Gulf Stream, black water full of tuna and typhoon energy. The Agulhas current off South Africa shoots warm Indian Ocean water down the coast so fast that huge eddies spin off and carry tropical species into the Atlantic, sometimes seeding new populations of corals and fish thousands of kilometers from home. Under the surface currents are countercurrents, undercurrents, deep western boundary currents. The ocean is a three-dimensional labyrinth of flowing water. Eddies are the weather systems of the deep. Some are warm core rings pinched off the Gulf Stream, swirling masses of sargassum weed and mahi-mahi that drift for months. Others are cold core eddies full of nutrients that feed explosive plankton blooms. The largest, in the South Pacific, can be 300 kilometers across and last a year. Internal waves move along picnic lines, density layers inside the ocean. They can be 200 meters high, taller than any surface storm wave, yet invisible from above. They break like surf on underwater slopes and mix water the way wind mixes air. Tides are not just at the coast. In the open ocean they lift and lower the entire water column by a meter or two. But because the wavelength is thousands of kilometers, you never notice unless you are in a submarine. In some places, like the Bay of Fundy or the Bristol Channel, geography funnels the tide into monsters 40 feet high, reversing entire rivers. The moon is slowly moving away from Earth, and the day is getting longer. 400 million years ago, a day was 22 hours, and there were 400 days in a year. The tides were stronger, the mixing more violent. Fossils show ripple marks on ancient seabeds that could only have been made by tides we cannot imagine today. Sound behaves differently underwater. It travels 5 times faster than in air and almost without loss over huge distances. The SOFAR channel, the sound fixing and ranging layer, sits around 1,000 meters depth where temperature and pressure create a waveguide. A hydrophone there can hear a 1 kilogram explosive dropped on the other side of the planet. Whales use it as a telephone line. Blue whales calling off Antarctica have been recorded in the North Atlantic. The U.S. Navy used it for decades to locate downed pilots. A special bomb would sink to the channel and detonate, sending a signal rescuers could triangulate from half a world away. The ocean is loud. Shrimp in tropical reefs snap their claws so hard that the cavitation bubbles reach thousands of degrees for a microsecond, loud enough to deafen submarines. A healthy reef at night sounds like frying bacon. Add whale songs, dolphin clicks, ship engines, sonar pings, and seismic air guns, and the deep is no longer the silent world Cousteau imagined. Bioluminescence has evolved independently at least 40 times. Some fish make their own light with symbiotic bacteria housed in special organs. Others eat glowing prey and repurpose the chemicals. Some squid squirt glowing clouds like ink. Comb jellies create rippling rainbows by diffracting light through moving cilia. Not chemistry at all. The Milky Sea's phenomenon, entire ocean basins glowing soft white for days, is caused by trillions of bioluminescent bacteria blooming at once. Sailors have reported it for centuries. Satellites finally confirmed it in the last 20 years. Chemistry down deep is alien. The water itself is not pure H2O. It carries 35 grams of salt per liter on average, mostly sodium chloride but also magnesium, sulfate, calcium, potassium, and dozens of trace elements. Some trenches have brines 5 times saltier, dense enough to form underwater lakes with sharp boundaries and even waves on their surface. Dissolved gases change with depth. Oxygen peaks around 1,000 meters where cold sinking water meets the last remnants of photosynthesis, then drops in the oxygen minimum zone where bacteria consume everything that falls. Below 4,000 meters it rises again as Antarctic bottom water brings fresh oxygen to the abyss. Carbon dioxide increases steadily with depth because it is produced by respiration and dissolution of calcium carbonate shells. The deep ocean is the largest active carbon reservoir on Earth, holding 50 times more carbon than the atmosphere. Methane clathrates, ice that burns, coat continental slopes in lattices of frozen water and methane. 1 cubic meter can release 160 cubic meters of gas if warmed. Trillions of tons are locked up down there. If too much destabilizes at once, it could accelerate warming dramatically. Radioactive elements tell stories. Carbon-14 from nuclear tests in the 1950s and 60s has penetrated to 3,000 meters already, labeling an entire generation of deep-sea corals. Tritium from the same tests is used to trace water masses. Uranium from seawater is slowly incorporated into the teeth of sharks, giving a timeline of how long they have been swimming. Pressure shapes everything. At 10,000 meters, every square centimeter supports a ton of water. Cell membranes would rupture, proteins unfold, gases compress into liquids. Deep animals have piezolites, small organic molecules that stabilize proteins under pressure. Their membranes are rich in unsaturated fats that stay flexible when normal fats would solidify. Some enzymes from trench bacteria work better at 1,000 atmospheres than at 1. Bring them to the surface and they fall apart. Minerals precipitate in strange ways. Manganese nodules litter the abyssal plains, growing a few millimeters per million years by accreting metals from seawater. Some are the size of potatoes and contain nickel, cobalt, copper, and rare earths worth hundreds of dollars per kilogram. The Clarion-Clipperton Zone alone may hold more metal than all land reserves combined. Mining companies are already testing giant vacuum cleaners to suck them up, raising clouds of sediment that may take decades to settle. Polymetallic sulfides around black smokers are even richer. Gold, silver, copper, zinc, deposited when 400-degree water hits cold seawater. A single chimney can contain or worth millions. Ferromanganese crusts coat seamounts in layers centimeters thick, growing even slower than nodules. Cobalt-rich, they are the target of the next resource rush. Life finds a way to eat all of it. Bacteria oxidize manganese for energy. Worms and snails graze the crusts. The Hadal Zone, deeper than 6,000 meters, covers only 1 to 2% of the seafloor, but is home to its own endemic species. Of the 37 known Hadal trenches, 27 are in the Pacific. Each is a closed universe. The Japan Trench has different amphipods from the Isobonan Trench just a few hundred kilometers away. Evolution works fast when populations are tiny and isolated. The deepest fish ever caught was an abyssal grenadier at 8,370 meters in the Mariana Trench in 2023. The deepest octopus was filmed at 8,500 meters in the Java Trench in 2024, sitting calmly as the pressure tried to crush the camera housing. We have sampled fewer than half the trenches with modern equipment. Some, like the Diamantina Trench in the Indian Ocean, have never had a lander touch bottom. Wood falls, whale falls, kelp falls, create oases in the desert of mud. A single redwood log that washes out of a California river can feed an entire ecosystem for 80 years. Shipwrecks do the same. The Titanic is being eaten by rustic-less, bacterial iron structures that look like dripping orange stalactites. In a few centuries, the hull will collapse into a pile of rust. Ancient wrecks in the Black Sea are perfectly preserved below the anoxic layer. Byzantine galleys sit upright with cargo intact, wood untouched for 1,500 years. Plastic is now part of the geological record. Microplastics have been found in sediment cores going back to the 1950s, a clear marker horizon for the Anthropocene. Fishing has reshaped entire ecosystems. Orange roughy stocks collapsed in the 1990s. Patagonian toothfish, marketed as Chilean sea bass, dropped 90% in a decade. Deep-sea sharks are caught for liver oil and take decades to recover. Bottom trawling has plowed the continental slopes so many times that some areas look like bombed battlefields. Corals 1,000 years old are smashed for a few kilos of fish. Yet new protected areas are being created. The Ross Sea off Antarctica became the world's largest marine reserve in 2017. Seamount chains are being closed to trawling. The High Seas Treaty signed in 2023 finally allows protection beyond national jurisdiction. Hope and destruction run on parallel tracks. Every year we learn something that forces us to rewrite the textbooks. 2025 expeditions found liquid water caves under the Thwaites Glacier in Antarctica, full of life cut off from the surface for possibly millions of years. Shrimp-like amphipods and anemones attached to rocks, living off chemosynthesis in total darkness. A new vent field was discovered in the Arctic mid-ocean ridge at 85 degrees north, the northernmost ever, with white smokers and dense animal communities under permanent ice. A population of blue whales in the Indian Ocean was found singing a completely different song from all other populations, suggesting they have been isolated for thousands of years. Environmental DNA from a single seawater sample in the Pacific revealed the genetic signature of a fish species thought extinct since the Pleistocene. The ocean still has the power to astonish us every single time we look properly. And we have barely looked. Less than 1% of the deep seafloor has been seen with human eyes or cameras. Less than 1,000th of 1% has been sampled biologically. The volume of water we have explored in any detail is smaller than a single coral atoll. The rest is darkness, pressure, cold, and life beyond counting. It is the largest wilderness left on Earth, and it is right here, surrounding us, keeping the planet alive while we argue about the surface of a planet we can actually see. The waves keep rolling in, carrying secrets older than bones and newer than tomorrow. And the deep keeps waiting,